What we've got here is, in Chapter 1A, we're going to go over some definitions, terminology, and basic concepts of this area specifically. Okay, so let's take a look at where we get, essentially, electromagnetic interference from. And this is kind of just a diagram to show you where it can always come from or where it may or may not come from. And we look at the center square and we see a source. And that source can either be specifically can be radiation from that, or the source can provide what we call conducted radiation, which effectively is through the power line itself, which then can couple to the different particular items we see specifically here. Now, if we take a look in victim A, we can see that we're getting possibly a conducted emission coming from the interconnecting cable, which means that source is generating energy that's coupled into the interconnecting cable. Now, that could either be done by directly having energy going down through there, or internally in the source, it could be capacitive coupling. Capacitive coupling is one of the main ways we can couple energy from one place to the other. Now, if you look at victim A over here, you'll see this dotted capacitance. That's the way that we indicate essentially stray capacitance, or effectively parasitic capacitance that exists between that. So you can actually get coupling from your power line, as you can see here, directly to some other victim or device through the capacitive coupling. Now, this means that you could, in fact, couple through a battery-powered device, couldn't you? You're standing there making a measurement specifically. Energy can couple through your capacitance directly into that unit. And that happens quite a bit specifically. Now, you'll notice also here on the source here, looking at the conducted emission going down that line over to effectively victim B, it's directly coupled. Now, the amount of energy coupling directly back to victim B can be significant because it's directly coupled versus the stray capacitance would be a portion of it. So you can see that you can either get radiated susceptibility as far as this victim shows. You can see that victim A also can get from radiation from its source. And that's typically through the aspect that some of the parts and components are positioned in such a way that it'll actually take and couple directly to it like an antenna. And that can be at various frequencies or a band of frequencies specifically on it. If we look at EMI and radio frequency interference, we can see that on this level here, going around here, you can see that we have radio and TV. Back in those days, we actually used the term RFI, radio frequency interference, because that was what they were interested in. In the United States, when it comes to building some sort of piece of commercial equipment, typically they only care about whether it interferes with the radio or TV. Unless you're doing like a mil spec specifically that we have, that's a lot more tight. But if you're developing your products for the European marketplace, they have a lot broader range, a lot more tests you have to be concerned with, versus what you have to be concerned with here in the commercial.
Is that called the CE mark?
What's that?
The CE mark.
The CE mark. That also has some interesting connotations with respect to China, which we'll explore later when we talk about the testing itself. Now, you notice that we're going from DC to 1,000 gigahertz specifically, so you can have interference over that whole band range. And then when you look at the European specs specifically, they're more interested in that than they are in the U.S., unless you're doing mil spec kind of stuff. The term EMI takes electromagnetic interference, takes in that whole spectrum. Whereas many times you'll see RFI, radio frequency interference, and of course the TV itself. Now, here's some examples of where we have had EMI problems. Electronic games, which are fairly popular, and the original electronic games that came out, like Pong and the ones after that, weren't really shielded too well. So in some cases, the electronic games would interfere with the police communication interference. It'd create noise, cause a problem in that area. Now, another case here, there's been cash registers, a mile away from the airport, and depending on what position it is, like for instance, it might be positioned where it's kind of just horizontal here, and then if someone shifts at 90 degrees, then it could interfere. So you've got a lot of situations like that. And of course, this is an actual case where an instrument panel on an aircraft has a sign that says, "Ignore all instruments while transmitting high frequency." And this has happened in the past. Of course, today they're doing a much, much better job of shielding and making sure the circuits don't really take off. Now, one thing I'd like to point out to you is if you look at your book, you'll see an explanation of for the HMS Sheffield. It's in the comments specifically, where if you remember, or maybe you read in the history, it's probably history now, is that an Exorcist missile fired about 20 miles away from the ship sank it. And the reason it sank it is because the actual system that you turn on to detect the missile would interfere with the communication system. So it was turned off, and because it was off, it sank the ship. That's quite a disastrous situation, showing you what EMI can cause. Now, all kinds of electrical noise sources are around us today, in big time, for instance. Calculators, electrical coils. Sewing machines used to be totally mechanical. Today, they're almost totally electrical, and if you go out and get a Bernina, and you get all the software that comes with it, you can spend close to $20,000 or more for a sewing machine. You really have to love that wife to let her do that, don't you? Specifically. Of course, a loose fuse causes some arcing specifically, and that arcing is like a little lightning pulse. I don't know if you've ever heard the term impulse function before or not. The theoretical impulse function, theoretical, is infinite amplitude at in zero time. And what happens when you do that is you generate frequencies from minus infinity to plus infinity. That's theoretical, but if you take a look at a little spark specifically, you'll get quite a wide frequency range of signals that aren't supposed to be there. So anything that causes a spark like that will do that. And of course, you've got electronic fences, lights, computers, video games, furnace controls, and we're getting more and more heating pads, fans. The heating pads are turned on and off, aren't they? When they turn on, because of drawing off the actual power, it creates a possible unstable aspect of that. So they're all over the place. Gordon, can you think of a possibility of something we have mentioned here that has maybe some sort of noise source?
Computers.
Well, computers would definitely do that, that's for sure.
I'm thinking where I'm working, I guess, is what we're getting at. What about fluorescent lighting?
Well, fluorescent lighting specifically can cause that. Because in a fluorescent light, what you've got is you've got essentially two electrodes that excite a gas. And that gas does emit some frequencies. You can actually see it to some degree. Thank you.
What kind of lighting would be the best lighting?
Well, it depends. But there's been cases where people have had noise problems and they could not figure out what the problem was. For example, this company was doing some testing of extremely low-level signals, actually it was electronics on the Hubble telescope. And they had their equipment within the room and they were trying to find the signal they were looking for. They couldn't find it. So after about 30, 40 days of playing around with it, they decided maybe the room's contributing to the noise. You know how you have benches around a room with equipment and that kind of stuff, interconnecting cables. So they decided to move all of that to the center of the room. Drill about 5 or 6 holes and put in grounding rods specifically at that point, right directly through, trying to find a common point. You don't end up with a ground loop, because you can actually end up with a ground loop problem on your benches as you scatter them around the doggone room. Not only that, if you take a look at the wiring in the wall, what kind of wiring typically do you have? You typically have AC, don't you? 60 hertz AC. A lot of times you'll get 60 hertz and 120 hertz as being noise problems, which can be fairly significant. If you look even in this room, you've got fluorescent lights above you. So by moving all the equipment to the center of the room, they're able to take and have only the people that were necessary in the room. Because as you walk around, you're a capacitance to change the coupling. You guys ever use a rabbit ear antenna? The type where you take and adjust specifically? And if you go up and you take and adjust it, for instance, my wife used to like this station, and when I was in the Los Angeles area, we didn't even need cable TV because they had all the transmitters on Mel Wilson. You got good, strong signals. But it just so happens that the channel she wanted to listen to, we had rabbit ears on, and I'd walk up and adjust it through my capacitance. I'm holding on to it, right? I'm adjusting it. As soon as I let go of it, the channel goes wacko. So I had to stand there for about 20 minutes one time to keep her happy, if you know how that goes, specifically. So that's a good example of a situation where minimizing the number of people, moving the equipment away from the AC lines, and turning the lights off tend to help make more precise measurements specifically. So you have to look at those as interference sources that exist there. Now the types of interference that you can have are spurious emissions, fundamental overload. A fundamental overload is one of the main areas. That's when you take and drive an amplifier into saturation, as an example, where your signal is too strong and it tends to move it into a nonlinear area in the amplifier or other places, and that creates a lot of noise specifically. And you have the external noise that can couple through from the outside into your unit. And then you've got the self-generated interference, meaning that the oscillators and high-speed circuitry within your circuitry is creating the interference. Or you could have defective consumer equipment, which is very easy to happen, by the way. Example of that situation is that I had my computer, I needed more power supply because the way it was connected, it would easily break at that point. And it was actually a poor design when you get right down to it. So I decided to look on the internet for different power supplies, and I found, gee, one $6, the other one $12. Of course, if you go down to the local store, they're $75. For instance, like the Hewlett-Packard unit. And so I actually bought 3 different ones to try to check them out. And it turns out the cheap one, if you plug that one in, you get interference and you'd be off the wall practically. So it's kind of like you get what you pay for. So here's actually defective consumer equipment. They even put the CE mark and everything else. And guess where it was from? China. So you've got to be very careful of that. And of course you have interference caused by someone else, which is maybe someone in the next room from you has a system, maybe a computer system they're running, and it interferes with your testing specifically. And of course, there usually can be more than one cause, with 3 factors. The trick is to try to find out which one it is specifically on that. Have you ever seen EED, Electro-Explosive Devices? Have you ever worked with that? If you take a look at this particular wave, this represents a magnetic field. And anytime magnetic field moves to a conductor, which is copper wire and or steel or large metal structure, it'll create an internal current. And that internal current, if these 2 pieces of metal actually are just touching off and on, intermittent, it'll cause a spark or an arc directly. If they're welded together and they're solid, it'll just create a current, which will not actually create the spark, but it's these 2 pieces of metal together that are not joined really tightly. And you've got cases where, for instance, have you ever been in a flour mill? Ever notice what happens when you take a handful of flour, the cooking flour that you got, throw it to a Bunsen burner or a flame, basically have an explosion. And an oil well example is that if you have a large electromagnetic field, which can be caused from a lightning storm specifically, it can induce these currents that will cause the sparks, which cause the oil well to actually explode. That could have been part of what happened in the Bay Area a long time ago. So if you look at your main supply, That would be could be the main supply as the wall. Many times people are using batteries today, of course. They do have limits themselves. You'll get voltage variations, meaning it'll vary up and down, depending on the load specific. Or fluctuations could be the load also. Typically, when we talk about load, we usually mean current. We say a heavy load is a heavy current flow, or light load is a light current flow. And of course, voltage interruptions could be where something just stops quickly. That can happen on your main line or even your power supplies. And of course, waveform distortions can very easily happen. And when you have distortions, you'll end up with additional frequencies being there, sidebands that you may not want. They may be too powerful. They cause essentially interference with local radio stations. And like, for instance, on the HMS Sheffield, the reason that particular system to detect the missile was actually off is because it interfered with, effectively, the other communication system. Then you have transients and surges that exist. These are some of the things that you can have specifically on your power supply. How about high frequency, pulsed energy, or continuous? If you have a pulse, a quick pulse that goes back like that, that pulse will actually sometimes, if it's small enough in width, will essentially simulate an impulse function. And that'll create a lot of extra noise. Sometimes you end up getting effectively a lot of interference by using very high-speed logic. You can use something that's a lot less of a rise time on that. Of course, the ESD from a person or object. Anytime you walk or stand, or if you're standing still and you lift your foot or your arm up even in the air, you're going to charge. You're literally going to charge up and change potentials. And if you're standing there and you're looking at a particular meter they have and raise and lower your foot, you'll see it'll go up and down as far as your charge. So objects themselves can get essentially ESD, electrostatic discharge. For instance, that coffee cup you have over there. What type of coffee cup is that?
Styrofoam.
Styrofoam. Now when you reached over and touched that styrofoam cup, you had charges under your fingers and they got on that cup. And what will happen is that they won't discharge because they can't. So you have an individual charges that can affect electronics that you're working with. So if you're actually drinking coffee, you should probably be using a ceramic cup or something of that nature. It won't maintain that charge.
We're going to be for exposed electronics, correct? I mean, if the instrument's buttoned up.
It depends on how much shielding you have on the instrument itself. When you touch a piece of equipment, even though it's insulated specifically, and let's say that you have like a fiber that you've got that you're doing for the shielding, you'll still get current flows. And unless it's constructed properly, you'll end up causing a problem. Now, when we go through the electromagnetic compatibility design rules, you'll find how a lot of them will apply to ESD also. If you follow these rules, it'll work out pretty darn well. You know, certain rules of thumb that exist specifically there. Then you can have low frequency fields. And what's one of the main low frequency fields we have? 60 hertz, right? Or 50 hertz. Now you got 60 hertz in the wall here. Have you ever noticed the aircraft uses 400 hertz? You have an idea why it uses 400 hertz?
That's smaller transformer.
Absolutely correct. If you take a look at a gigantic transformer 60 hertz, when you look at an aircraft transformer 400 hertz, it's much smaller, which means it's a lot lighter, specifically on that. Now, one of the problems we have today is how much software do we end up having in our systems? Well, what's the latest scandal with effectively, gee, I can't think of the company. The Volkswagen, specifically on that. What's the latest scandal on that? Use software to determine whether they're being tested or not, to change all the parameters so that they're able to take looked like they had a lot less emissions. Software can be really a problem. It's this faulty software can look like an EMI problem. So it's all interconnected. And you notice the symptoms can be identical to those induced by EMI. You have system crashes, you get faulty data, incorrect program flow. For instance, in every computer, there's a thing called a program counter. The program counter is pointing to where it wants to get the next instruction. And if you happen to walk up to it and touch it in such a way, maybe that software causes it to advance the program counter when it's not supposed to. So you've got these kinds of things. So software becomes an issue that you have to look at, especially since over 50% of it's software now, isn't it? If you look at the modern day electronics, almost everything has a microprocessor. Your microprocessors were introduced to really around 1970, 71, maybe a little bit before, a little bit after. But the main microprocessor that really moved things forward was the Intel 8080, specifically on that. It's kind of funny that I did a little research on that. And Hewlett-Packard came out with what they call the 2640 series terminals for the computer systems. Prior to that, you used teleprinters. Or if you took and used a CRT, you ended up spending about $5,000 just for the little terminal. So HP brought out the 2640s, which happened to use Intel 8080s. That actually is what put Intel on the map. Large orders they received for that particular processor. So that's mainly where it started, right? In the late 60s, early 70s specifically. The other thing, too, is today we use plastic cases. If you look at the electronics of World War II, it's big steel tanks practically. Everything was sealed, and that worked out pretty well. But plastic cases, even though they use some sort of foil on it, or wire mesh on the inside specifically, or try to scatter metals within the actual plastic itself when they construct it for shielding, you still have a lot of holes. So a lot of energy does get out or in, depending on what's going on.
On a fault plate.
What's that again?
Fault plate? Not plastic, but it's like plastic like stuff.
Yes. And one of the biggest sources of errors and noise is essentially switching power supply. Switching power supplies are those power supplies that were actually pretty much been known, but really practically created, right? Well, I'd say about the middle to the last part of the 70s, switching power supplies. And what the switching power supply does, it allows a much powerful power supply in a much smaller space. And how many of you have a laptop? You here, I can't see whether Jay Harry does, but anyway, that's what they probably do. You know the power supply you hook up to charge the battery? Even though you don't realize that that's a switching power supply. The switching power supply creates lots and lots of noise, lots of interference with your actual power lines themselves. Remember I told you about the $6 one that I had? It caused a big time problem. And the electric power companies have to maintain a certain stability, frequency. It's getting very, very difficult for them, so they're working on actually charging tax larger companies depending on how many switching power supplies they have hooked up. What they'll probably do is guesstimate it, charge an additional actual amount. You can see right here that size reduction. If you take a look at the original cell phones, they're about the size of a small briefcase. As you make things smaller and smaller and smaller, parts get closer and closer together. You get coupling. A size reduction creates a situation on that. So EMC has two parts: operate without interfering, and the other thing is to operate as indicated in a specific electromagnetic environment. Now, one of the worst electromagnetic environments is a Navy ship. Take a look at a carrier, take a look at a destroyer, take a look at the variety of the different classes. There's lots of electronics involved, lots of radar involved, and there's noise all over the place. And so you need to when you design something for that environment, it has to be able to operate and not have a situation where you had on that one example of when you take and have the RF frequency, don't worry about the instrumentation, it'll pass specifically on that. So this is what we have to look at. Now what can cause interference? Now if you take a look, this is showing you that you've got some sort of signal source certain distance from ground clutter. That could be the shape of the hills, it could be that, and then of course when you get into a building environment, you have lots of buildings, like down here on the strip, or if you go to New York and a variety of places like that, you look around, you'll see a tremendous number of antennas, essentially your cell antennas. Small antennas scattered all over the place, because one big antenna won't do it. So what happens is this energy goes along here, and it reflects off the buildings at different frequencies, and that can cause interference in itself. The main signal you're working with. So you've got this situation that you can cause a lot of interference by the energy coming in and hitting and bouncing off these buildings. That's why you have one big antenna and then you have many small ones here picking it up and boosting the signal if they want to. This is showing you that we have a frequency range of 30 megahertz, 300 megahertz, and you have a median field strength equal to F over D to the N. And D is the distance. And the N, depending on whether it's open country, is 1.3 or 2.8 for built-up urban areas. And a lot of times what they'll do is they'll use an average 2.2 for approximate estimate. As you can see, as this distance changes, varies, the further we get away from the antenna, the field strength will be less and less. So we have this variance. What's interesting about cell phone technology is supposedly we should be able to detect aircraft that's effectively shielded quite well by the variation in the signals that you have on your cell phones. As you will, you have radar paints and shapes that cause the radar to be reflected at other angles rather than back. So they've come up with techniques where you actually can fly aircraft through an area where a bunch of cell phones are located and see the aircraft, even though it's invisible to radar. So you can see how these field strengths can vary and cause an interesting range. Now, if we take a look at situation here, primary cause of interference is overload. What we mean by that is maybe a signal comes in to your equipment. It's too strong, really strong, and causes it to force your electronic circuitry to go into an overload condition. That can happen very easily, even in a test system. If you're looking at a data acquisition system, you're looking at a transducer right here, and then it converts the signal into voltage. And if something unexpected event can happen, it can take and drive the transducer to saturation, which creates an overload condition. And you also can see that this particular equipment can be overloaded also by an external frequency, or connecting cables, or through the capacitive coupling of the equipment itself. A variety of ways for it to couple. Now, if you take a look at the schematic there, typical schematic, the trouble is a lot of times we don't even see schematics anymore. You see block diagrams, and this is what makes up the circuit. But what happens here is, this is just a rough plan, guys. What happens here is that if you look at this resistor and this capacitor together, they form effectively a network or a resonant circuit. They can resonate at other frequencies, and you can determine what they are. It's nothing more than a rough plan. There's no geometric information as to where to position these things. Many times when you take and lay it out on the card the way it is in the schematic, it'll cause a lot of interference. So when it comes to layout, the geometric aspect is really important. How big are the wires? How wide are the traces? How narrow are the traces? Where is to be turned to that particular current flow? What is the connection sequence you're going to go through? And of course, the component orientation. If we look at this, this visibly shows you here two inductors. Notice that they're not in parallel, but they're also not perpendicular to each other. If they were perpendicular to each other, there'd be no coupling, or very, very minimal coupling. If you have them parallel to each other, such as this, there'll be a tremendous amount of coupling that exists between them. You can see that it's at an angle to this coupling. So just the layout can cause a problem. Now, one of the problems you have is with PC cards is autorouters. You can almost say that autorouter maximizes the EMC problems. Because what they're doing, trying to do is typically save space, save material, like minimize the amount of copper used on the board. Well, you'll find out that you should maximize the amount of copper. Keep your ground planes where there's less space between them, because it creates a smaller loop area, as we call it. Now, if we take a look at components and see how it can vary specifically, here's a piece of wire. Now, low frequency would be considered as just having essentially a resistance. If you're looking at low resistive values, many times you make measurements, ohmic measures, what we call 4-wire measurements. 4-wire measurement is there's two sense leads that actually couple across it to take the actual resistance of a wire out. You're measuring a component. But as we move up higher in frequency, as you can see specifically on this chart here, that if we plotted the blue, that's what we would assume it would be. But as we get higher and higher in frequency, the inductive reactance gets bigger. And it reaches a point to where you actually have a resonance circuit. So you actually, impedance looks like this, not like the blue line. Take this capacitor. We still use a lot of capacitors like this in circuits. Many of them actually are board numbered or right on strip line or things like this. The reason, of course, is to reduce the length of the wiring, which you can see here. This is our symbol for our capacitance. And then again, what happens here is you've got wires here. That creates the inductive aspect. And so we end up with effectively a tank circuit. The Z would normally go like this, down. But because of that inductance, it creates that red situation where we actually end up with it forming that shape. And these can interfere with circuits, create problems. Here's an inductor. And an inductor specifically. It looks like this, but what will happen is you actually have capacitance between the windings. Windings themselves. So you end up with a parallel circuit, which you can see takes on this form, specifically the higher we get in frequency. Of course, you'd think of a carbon resistor, that doesn't have much with it. There's what it looks like. There's the actual schematic symbol. And then here you'll see the inductance is due to the wires themselves. And then the actual resistor itself, there's a capacitance between the two ends. That little piece of metal connecting on that end, and this capacitance. So you end up with this kind of arrangement specifically on there. Okay, so about 5 minutes after the hour, so why don't we take a 10-minute break? You're able to get your coffee, whatever it may be, specifically. And then we'll start up on electrostatics.
Sounds good.